Okay, so when I see the word fission, I think of the word fissure, like a big crack. Got the same root word, fissure, because fission is when you take a nucleus and it's falling apart into big pieces. Now, this right here is not fission, because it doesn't meet that definition. But it's there for a reason. So the most common place where we use fission is with uranium. And a specific kind of uranium, uranium-235. Okay? Specific isotope of it. It's the one it's the most radioactive of the ones you're going to find around. Okay? And it turns out if you shoot a neutron into uranium-235, well, that neutron doesn't have a charge, so it won't be repelled by the nucleus. And if it gets close enough, the strong nuclear force is going to be able to hang on to it. Right? And I'll turn uranium-235 into uranium-236. Now, uranium-236 is really unstable. And it falls apart. So uranium-236 I make, it goes through fission. And I get two new kinds of atoms, barium atoms and krypton atoms. This is only one of the things that uranium-236 falls apart into, because that unstable nucleus starts shaking around and it shakes itself into two big pieces. So you have to start with a pretty large atom before it can do alpha decay. Or before it can do fission. It's got to be pretty big before it can do fission. And it makes big atoms. But one of the most important piece is, there's actually two of them. The first is that this gives us a whole bunch of energy. And the energy here comes from the same place it always comes from. Mass gets destroyed. How much energy are we talking about? Well, if you had a kilogram of uranium-235 that went through this change, it would release as much energy as blowing up 20,000 tons of dynamite. That's how you make an atom bomb, is you change what kind of atoms you have. So this is the change that happens inside an atom bomb. Okay? And 1 kilogram gives you enough energy for 20,000 tons of the lot. Okay? But the secret ingredient is right here. Those three neutrons. Because if I put in 1 neutron, in the end I get 3 neutrons. But that's 1 neutron hitting 1 atom. I'm not going to have just 1 atom. Those other neutrons are going to be able to hit other atoms and change them into uranium-236, which will then fall apart. Okay? So first I'll have 1 fall apart, I'll make 3 neutrons, then those 3 neutrons will hit, and I'll make 9 neutrons, right? Because 3 from each one. And then those 9 will hit, and I'll make 27 neutrons. And then those 27 will hit, and I'll make 81 neutrons. Then 81 will hit, and I'll make 243 neutrons. Then those 243 will hit, and I'll make 729. And then I'll make 21 to 57. The numbers start getting big pretty fast, right? That is a chain reaction. A chain reaction happens when the neutrons that you make start the process for the next one, which makes more neutrons, which starts the next one, which makes more neutrons. The simplest model I've seen that shows this is this. This is a board covered in mouse traps. And they're all set. And a couple little pieces, and on top it's got little pieces of wood on top of the arm. So when the mousetrap gets set off, it's going to throw things in the air. Okay, so watch what happens when you throw something on. Well, the first one you throw on does nothing, but the second one, how come the first one didn't do anything? Well, it's not that it missed. If you look carefully, it hit a mousetrap. But it didn't send any others that hit. The key is when the second one hits, see those two coming off? Watch where they land. Okay? So the key is getting those wooden blocks to hit the other wooden blocks. The key is getting the neutrons to hit other atoms. So at the atom scale, where's it at? I had it running. Oh. That's not the one. Huh. There it is. Okay, so, all right, so here I have uranium-235, and this is a neutron gun that shoots one neutron. It turns to 136, and that 236 falls apart. And it makes 3 neutrons. See all the pieces coming flying? Okay, so if I have more than one of these, how come there's no chain reaction? Didn't hit any other ones. Didn't hit any other ones, did it? So I need more of them so it can hit more of them, right? Everybody agree that's what I need is more uranium-235 ones. So let's put some more uranium-235. Okay, so more of them reacted. That was a nice slow chain reaction. What happens if I put 50 in? $50 was faster than 25. That's kind of strange, isn't it? Okay, so the whole secret is, notice I used them all up this time too. The whole secret is I've got to get those neutrons to hit. Now there is another way you can do it. We saw that 15 didn't work very well, but if I put it inside a container, got to hit one of them. Probably won't miss that one. Notice the neutrons. Okay, the neutrons stay inside that container, so my 15 worked. I didn't need as many. But if I seal it in a container, it works better. Yeah. Okay. So the closer together they are, the more I get them to react, get those neutrons to hit, the faster this is going to go. That's a chain reaction. Okay, so picture, same thing. Neutron hits uranium-235. It makes lighter elements and 3 neutrons that hit uranium-235. That make those 2 lighter elements and more neutrons. Okay, so in order for this to get out of control, you need a chain reaction It makes that happen. Yeah. Okay, so what can you do with this? Yeah. When they first recognized things can get out of control, they built these two things. The top one is a little boy, the first nuclear weapon dropped. The second one is Fat Man, the second nuclear weapon dropped. And that's what the cloud, so this is where the clouds are at, and that goes above it. That mushroom cloud is because it's just heating up so fast. You get hot air rises, and really hot air rises really fast and really far. Okay, so how to build a bomb. Make those neutrons hit other atoms. That's what you do. And the easiest way to do that is the containment pistol. All you have to do is to put enough uranium-235 or enough plutonium into a sealed container. When you close the door, it'll get out of control and blow up on you. Because they're close enough. Once you get to 22 kilograms, you got enough that they're all going to hit.
So plutonium like the easier material to use?
Yeah, except it doesn't occur in nature, so you got to make it in a nuclear reactor first. So you got to start with uranium-235 so you can make the plutonium that you can make the plutonium to, because plutonium doesn't exist in nature. Yeah. Okay. I mean, they found this like they were reprocessing fuel in Japan, and somebody closed an air vent, and that was the last door that had to be closed before things went out of control inside that room. Okay? It really is just lock it in the same place, it gets out of control. Okay? And that was and this was the idea behind that first bomb, the little boy. All it is, it's a long, skinny thing because what's inside of there is a howitzer, a cannon. And they made the shell of the cannon out of uranium, less than 22 kilograms. And at the target end of the cannon, they put another piece of uranium, less than 22 kilograms. So when the bomb dropped, just before it hit the ground, they fired the gun. The gun shot the shell into the other piece of uranium. You now have more than 22 kilograms in the same place, and it blows up. That's how the first bomb worked. Okay? But uranium-235, getting it away from finding it in nature is really hard. So when they could get plutonium, they could get a higher percentage of the plutonium. They made the second bomb, but the second plutonium bomb doesn't work the same way. They found it was more efficient to move the atoms closer together. If I make the atoms closer together, they're going to hit more often. So what I have to do is I have to squeeze a piece of metal. Well, you're not going to use a piece of machinery to squeeze a piece of metal closer together. So what they did was they took a core and surrounded it with high explosives on all sides. Those high explosives are shaped charges with everything designed to blow inward. So when they all go off at exactly the same time, all the force goes in and that piece of plutonium gets pushed closer together. And then they shoot neutrons at it. Does that make sense? Once I get them closer together and I shoot neutrons, they're all going to hit. Okay? So that's what it takes to build an atom bomb. Doesn't seem really hard, does it? What's the hard part? The hard part is getting the material. Okay? Because when you go dig uranium out of the ground, it's about 1% uranium-235, 99% uranium-238. So most of it is stuff you don't want, uranium-238. And the only difference between uranium-235 and uranium-238 is uranium-235 is 1% lighter. Right? And it's about 1% lighter. So during World War II, what they used to get that was they used that mass spectrometer and separated one atom at a time because the 238 bent less than the 235 because 235 is easy to turn. So they took one atom at a time, charged them, and saw how they bent, caught the ones that bent more. That would be 235. Current method is to use centrifuges. Make a liquid out of the uranium, have it react with something to make a liquid, and then spin it really fast. With all those extra G's, the 238 tends to go toward the bottom of it, and the top tends to be more 235 because it's lighter. They take the stuff off the top. It's a little higher percentage 235, and they take that and they put that into a centrifuge. And they spin that centrifuge. The bottom's more 238, the top's more 235. They take the top of that and move it into a centrifuge. So you use a cascade, one centrifuge after the other, and gradually the percent of 235 goes up. You need to get it up to about 4% if you want to make a reactor. If you want a nuclear reactor, you need about 4%. Anything more than 4%, the only reason to go for more than 4% is because you want to build a bomb. So anything above 4% is safe for nuclear reactors. Anything above 4%, you're going for a bomb. So when you sample your stuff and it's at 8%, we know your goal is to make a bomb. Okay. So in Iran, we didn't want them to get the bomb. So in the first real example of international warfare, using technology, using hacking, they wrote a program that only worked on those centrifuges. And what it did was it copied the instrument readings for a few seconds and then fed those same instrument readings back to the display. So the guy watching the machine, watching the monitor, everything was normal. And once it started playing the normal stuff, it went and turned the centrifuges on and off really fast. And when you got something running at 200,000 RPMs, you do not want on and off real fast. It shakes it apart and sends things flying all over the room and destroys all the centrifuges. And that's what happened. It's called Stuxnet. They designed it just so those centrifuges, they knew which brand they were, just so those centrifuges would blow up. It only worked in those machines. Okay. Second hard part. If you want to go with the compressed with explosions, you've got to get all the explosions to go off at exactly the same time. Within nanoseconds, within milliseconds of each other, microseconds of each other. Because you want to squeeze that. And that means you got to push it evenly from all sides. If one side's a little bit late, the stuff's going to be shot out that direction. So you've got to have really good timers. So we don't sell technology to Iran. One of the technologies we don't sell is high-speed cameras. You know, the cameras that take 20,000 frames a second? That means they have to be able to time 20,000 frames a second and turn a light on and off 20,000 times a second. That's a really good switch. Good enough to make an atom bomb. We don't sell them those switches. We don't sell them stuff to do high-speed photography. Because this things are used for high-speed photography can be used to make an atom bomb. And what's it used for? The good side of it, a power plant. France gets over 50% of its electricity from nuclear power plants. We just closed, we're at the part where our nuclear power plants are reaching the end of their lives, and we still get over 10% of our electricity from nuclear power plants in the U.S. Okay. Nuclear power plants are great, no greenhouse gases, not going to warm the planet, carbon free. Okay. Like I say, use the same stuff, but less concentrated. And you want the chain reaction, but you don't want it to go out of control. So what you want to do is you want to design it in such a way that exactly one neutron hits for every neutron you put in. One neutron hits, the next it does all the changes, and out of those changes, one of those neutron hits. That's where you want to be, exactly 1 for 1. Because if it goes on average above 1, it's going to blow up. If it goes below 1, it's going to stop working. It's going to shut down. So you want it at exactly 1. Okay? So use stuff that absorbs neutrons, because that will control the speed of the neutrons. So they're moving slow. You don't want them flying through the nucleus. That would be bad. Or you want to stop them altogether. You want to absorb those neutrons. So you put in a starting set of neutrons, and then you want to control what happens from there. And the things they use are called control rods. Okay. Yeah, so you need to adjust it. You want to run a nuclear reactor so that there's 1 neutron out for every neutron in. One neutron hits for every neutron you put in. You get one out that's going to hit something. So you want to set up so it's absorbing the extras, but still letting enough through. Okay, so look at this, how the simulation does that. Okay, so you got a nuclear reactor, and they put these control rods, usually made out of boron, and oftentimes there's a whole bunch of water surrounding this stuff, because water will slow the neutrons down too. The water itself is not just cooling it, but actually uses as a moderator. Moderate how many neutrons get through. Okay, so you can slide these in and out. So because if I fire the neutrons while they're in, it's hard for it, it gets absorbed before it can do any real damage, and before very many can take off. The chain reaction can't take off. It starts off in there, but it's stopped because it gets absorbed by the control rods. Okay, so what you do is you want to have them out a little bit, and then get it started. It's not quite enough. Let's try again. Oops, come on, you can do it. Okay, once it starts making pretty steady power, I want to slow it down or speed it up. So you control how fast it goes by moving the control rods in and out. So I try to keep a pretty constant source of heat. Oh, I killed it off. Okay, so that's how you adjust a nuclear reactor in big scale. There's some finer details, but that's the big idea. Okay, but this is what they did in Chernobyl. Okay, so you got the nuclear reactor, and it's not producing very much power because it's the middle of the night. Suddenly, somebody says, I need a lot of power. How fast can I turn up this reactor so it makes lots of power? So this is what they were doing. So they pulled the control rods out, and it started going. Okay. And then once it started going really well and got to where the level, they were going to put the control rods in so they could control it from there. Except when they went to go put the control rods back in, it got going pretty well. They were going to put the control rods back in, and they wouldn't go because it got too hot and everything swelled up. And then the reactor went out of control. What happens is the fuel gets too hot. It melts, turns into liquid metal. That liquid metal is hot enough to melt its way out of the concrete at the bottom of it. It melted its way through the concrete at the bottom of the reactor, went into this little room below it, melted its way through the concrete floor. And when it fell through the concrete floor, the ground below, it happened to hit a wall. And some of the uranium went on one side, some of the uranium went on the other side. And now the uranium wasn't all in the same room anymore. And the reactions stopped being out of control because you separated your uraniums from each other so that they weren't hitting often enough. And they just got lucky at that point. Yeah. After having the reactor blow up on you, how are you calling that lucky? Well, It could have been worse. Okay, so what you do is that fuel is going to get hot. You don't want it to get too hot because the first thing it does is boil away the water, and that water was moderating. So now it's not moderated anymore. That's what happened in Fukushima. The tsunami knocked out their generators. The generator was there to run the pumps to circulate the cooling water. The electricity gets knocked off. The cooling water's not circulating, so it boils away. And now the neutrons aren't moderated, they're more likely to hit. And the reaction starts getting out of control. But the fuel gets hot, boiling water. And from that point forward, it's just a regular power plant. Boiling water, the steam turns to generator, generator makes electricity. Okay. Now, actually, got to be careful, there's two waters. There's water inside and there's water outside. The pink water is radioactive. It stays inside the generator all the time. The red and blue water is not radioactive. It doesn't have to, it gets only, all it does is get heated by the water from it gets heated by the radioactive water, but not touching it. The pipes run through each other. So you don't want this stuff to come out. The stuff on the outside is just regular water. So as long as you keep that big building sealed, everything should be contained. That's why it's called a containment building. Usually they have big smokestacks off by them that are all shaped like this. And that's just to cool off the water. It's a cooling tower so you can cool this water off. So you can send it back in to turn it into steam again. Okay. The opposite of fission is fusion. And in fusion, two heavy atoms are put together. Or two light atoms are put together to make a heavier atom. The opposite of fission is fusion. Fission is one big atom making two smaller atoms. Fusion is two small atoms making a bigger one. So two helium atoms running into each other, or two hydrogen atoms running into each other can make a helium atom. This is the reaction what's going on in the sun. This is where we get all our sunlight, all our energy from the sun from. And it's also where we get everything heavier than hydrogen. The Big Bang only made hydrogen. Everything heavier than hydrogen got made in a star. Because once you use up the hydrogen, then helium starts running into each other. And you can keep doing that and make heavier and heavier atoms all the way up to iron. You can make the atoms all the way up through number 26, iron, inside a star. But you can't make anything heavier because it needs to be hotter. So you need hotter than a star to make the stuff heavier. And what that is when a star explodes, a supernova. So all the elements heavier than iron, not just were made by a star, they were made by a star when it exploded. There's lots of those things you've heard of before because there's lots of them around. And they're all the remains of exploded stars. So you're made of stardust. So the two hydrogens come together and make a helium. You get much more energy output than fission. But it's got to be hot enough. You've got to get up to 1,000,000 degrees. That's the problem. What do I mean by more energy output? But you got to be 1,000,000 degrees. Well, we saw how an atom bomb was made. Well, one of the places where you can get temperatures above 1,000,000 degrees is in the middle of an atom bomb. So they took hydrogen and stuck it in the middle of an atom bomb. Now when the atom bomb blows up, it starts this in the hydrogen inside, and you get much more energy from that bomb. Those are called hydrogen bombs. And they're doing fusion instead of fission. And I said that atom bombs are measured in kilotons, how many thousands of tons of TNT. Hydrogen bombs are measured in megatons, how many millions of tons of TNT they replace. Okay. So, a few questions out of the book. Let's see you tomorrow.